I'll take through the process of starting a project, and then I'll take you through a project that has already been processed. So just so that it's easy to replicate on your end. Just a second. There we go. Okay, so I just opened up PhotoMesh and I did start new project. Usually it's better to locate the project in a place that you have enough storage and that you can locate the results in. Then loading the images in. They should also be, if you're going to run on multiple fusers, in a location that has easy access to. So let me load folders and I'll navigate to the unique project that we have the sample for. So here we are. We have the nadir and the oblique images over here. These are the 90-degree images, the 45-degree images. Let me just confirm that that is where the data should be. Here we go. Okay, so yeah, these are the 45 and these are the nadirs. So it's also easier if the data is located, if it is different oblique angles or different cameras, it should be in different folders. And then when you select the folder, it gives you the option to use each folder as a separate collection. What we refer to as a collection is when we run the aerial triangulation, we treat every collection as a different camera so that we calculate its own camera model, focal length, principal point, distortions. And usually, if data is collected over a course of several days, it's better to have each day as a separate collection. So let's see. We could jump to where some of the images are. Okay. Now, I think there's one image that didn't have a GPS location in there, but what I could do is, first of all, the icons might load a little bit too big, so you can go to the View tab, make them a little bit smaller, and then it's easier to view the these are the oblique images, and these are the nadir images. Okay, and I'll quickly draw the AT area, and then I'll show how it's possible to look at what the coverage is. And the AT area could have a lot of buffer around it. It's just the general location. And based on the footprint of the images, you see if any part of the footprint is inside the AT area, it gets used for calculating the process. So for example, if I did an AT area that was very small, over here it'll only use the images footprints that used in that area. You see the gray images don't hit that area, so they're not being used in the process. So out of 286 images or 285 images, it's only using 236. It's thrown out the ones that are pointing away. The ones that you see any part of the footprint touches that AT area do get applied in the AT calculation. For this demo, I'll just take a large buffer around the general AT area, something like this, and then all the images are applied in. Okay, now the other thing that is helpful to look at is if you look at a coverage map, and by the way, you can see that when we import the images, we import the XYZ and we translate the yaw pitch roll into omega phi kappa. We can also treat it as yaw pitch roll. So that's why we know the initial location and orientation of the images. So in the coverage map, you could create a coverage map. It calculates the multiple perspectives that hit each spot in the area. And based on that, you can see where you have good potential coverage for 3D. So let me turn off the images and we'll have a look. So over here is where there is full 5 directional coverage, meaning from nadir and at least 4 directions. Over here, there's still good coverage, but it's more of a 4 directional coverage. So it might be covered by nadir and 3 directions, but not necessarily the 4th direction of the oblique. So this gives you an idea of where you could produce good data from. Depending on what's your goal or what's the quality expectations, you can always take a bigger spare in the AT area, do something like this, and then calculate the coverage map, and then see wherever you have, let's say, more than 3 image coverage could be a good potential to at least produce a good dense point cloud and a good ortho. So you could create a reconstruction area that is, let's say, something like this. And then all of the outputs that get produced from the process get cropped to this area. Taking into account that the really good results will be here in the middle, but there still should be pretty decent results around this area. If you look at how it corresponds to the image coverage, over here, there wouldn't be any coverage from the outside, but it could be pretty good coverage from this angle and potentially from the top. You can see where some of the nadir image coverage covers this area. Okay, so that's how we set up a project. Once we're happy with pretty much just importing the images and assigning a reconstruction area, you could just go to build and build the complete project. Just to give you an idea, when you do build the project, if there are no fusers running, you could just hit build and it will automatically kick off a local fuser. I'm using a fuser pool, but just for this demonstration, I'll turn off the fuser pool. And you see when I press build, it'll give me a message that says there's no fuser running, and then I could launch a local fuser in order to get the process going. Additionally, there's always the option to launch a fuser from the desktop install, and it looks like this. It's just the PhotoMesh fuser executable. So if it runs, it'll launch this icon over here. Okay. Just for the sake of demonstration, I will. The working folder needs to be somewhere in a network location if you're running multiple fusers. If you're only running a single fuser, it only needs to be in a local area. And the working folder here needs to be the same as the working folder in the fuser. That's how the fusers communicate. So when I press build, before I hit the build process, I could make sure that I'm using the hold on, let me actually select it. Here we go. And now those fusers are available to run. When I press build, those fusers kick in. Okay. So now I'll open up this project that has already been processed. There it is. I'll turn off this fuser. Okay. So this is the way I configured the reconstruction area for this. And you see it's pretty much the same project. The image is imported. I just created a large AT area to cover everything and imported the images in. One thing to consider, you could see that sometimes if the images don't have very accurate GPS, you can see they come in at 2 different levels based on, you know, the Z value might not be perfect. So that's pretty common with drone data that doesn't have PPK. So one thing to consider is when the AT runs and that depends on the quality of the AT, but we have our GPS factor as 0.1, which means there's good freedom level. If it is PPK or if it has accurate GPS, you have the option in the build settings to change the AT to reliable, the camera position accuracy, and then it relies more on the GPS input. A standard GPS does give more freedom level, and we can see that after the calculation of the images, you see they line up because they were flown at the same altitude. It's just the GPS accuracy had some variation between the two flights. So once the calculation happens, you see the nadirs, the obliques. You can see the original location of the image and then the final location of the image. So it moved it into the right position. The nadirs shifted a little down, and the obliques shifted a little up. But at the end of the day, they're all correlated pretty well to one another. And we can look at the AT report. Once the process is done, you can view the calculated images, you click on the tile, or you can go over here to the build report and load the AT report. About 0.7 pixel residual, it's pretty decent. And here are the collection 1, collection 2 results, slightly different camera models. But overall pretty similar. And that's the results of the AT. The result of the reconstruction then, once the AT is done, it gets split up into tiles, and that's how the 3D processing can be split up into multiple computers. Each tile goes through a very robust dense point cloud extraction. So you see this is the dense point cloud that's extracted for this tile specifically. You can see the tiles have a buffer around them so that if you load in an additional tile, they all merge together pretty seamlessly. So this is point cloud from one tile, point cloud from another tile, and then the textured model from this tile and the textured model from this tile. At the end of the process, we merge everything together. You can see over here, this is where the tiles meet. It's a pretty seamless connection. There's really no gaps or anything that would create a visible artifact. And that's how, at the end of the process, we create one single 3D mesh for the entire data set. Looks like this. Now, one thing that gets done during the 3D extraction process is we extract the edges, direct extraction of linear features. So you can see wherever there are corners or straight lines, they have a connection of multiple features that then enable the edge to be much crisper, very straight. And that can also be visualized with the triangles on top of the mesh. The other thing that we're seeing is we create built-in pyramids. So you see when I zoom out, if I look, you see this is the pyramid level that is being displayed. If I zoom in on an area, it's going to load a higher level of pyramids, triangle density. And then when I zoom in, it's going to load pretty much the maximum triangle density at this zoom level. So, and you can see it take effect when you're viewing the mesh itself. As I zoom out, it's showing the low-res pyramids and texture. And then as I zoom in on an area, it brings in the highest resolution for the screen caching. You can see the effect of the edges and the linear features on the building extraction, and also the smaller features like chimneys. So that's part of the advantage of the PhotoMesh 3D extraction. Once the 3D is done, so first of all, it could be exported into 3DML and brought into TerraExplorer. There's also the option to export other formats in the PhotoMesh Pro version, as well as export the dense point cloud, either from the photo correlation or the 3D model, which is what we're seeing here in point cloud format. The true-ortho the DSM and the DTM. So a lot of additional outputs from the derivative products that the 3D mesh produces. So this is the same 3D mesh that we were just looking at, loaded into TerraExplorer. Now, what can be done is you can see we're bringing in background data. You could bring in your own orthos if you have them, or stream them in from WMS, WMTS, or from the Skyline Globe server as an MPT. But this is what we call a 2.5D product. So everything is inside the Skyline Globe. And we can load things such as borders and places, roads, and then we can zoom into the layer of interest. Okay, and we can turn off the roads and some of the other things if we need them. Okay, so once the 3D mesh is inside TerraExplorer, we could do a lot of different options, such as measure 3D areas, vertical areas, horizontal areas. So everything is measurable and has a geospatial, both location and geospatial reference. And just to demonstrate the measuring capability, when you measure an area, it can either be a arbitrary plane, so let's say a slope, or you could do it on a horizontal plane, and then it assumes that it's a plane, a planar feature, not necessarily a sloped feature. We also have the option to snap to the mesh so that it's easier to mark corners. So you see over here, I can use the snapping tool and then snap to the edges of the roof. And there's the 3D measurement for that 3D area. If you have this option checked on, create measurement objects, it creates this as an object so that when the process is done, you can just export all of these into either a Skyline format, fly file, or a KML, a geodatabase, a shapefile. So everything that gets measured or done is accumulated and then exportable. The other options for the software, you could simulate an aerial object in motion, and you could also add a 3D model or a moving car on the road and represent it. This is a moving view shed, so we can see what's visible from that location. You could also have a static view shed, so what a camera would see or what's the perspective from this corner. This gets done by adding a view shed. Even once the view shed is done, as a layer in the project tree, it can be edited. So this is my view shed. I could change the horizontal field of view or the vertical field of view. I could also, rotate it, move it around. So, or up or down. So everything is editable. Once you created it, you're not locked into that measurement. Once the view shed is in there, you could add things such as a potential building and see how, this building affects windows that might be on this building, or it could really be, any sort of analysis. It could also be from a moving car, and let's say if a car is parked over here, how it affects the parking lot. So there's a lot of 3D analytics, and also line of sight, typical line of sight. So if I want to see what's visible from, this is the observer, and then I could set, different target areas, see what's visible from where. So, and you can also use this by clicking the mesh and snapping to it, like I showed with the snapping tool. That also gets recorded as a layer here. The other thing that are possible to do, is you have different tools that allows you to, let's say, duplicate objects. If you want to populate multiple models such as trees or cars or people, I think I created a duplicate object of a forest over here. Oh, no, I just created some cars that are parked. And I think this is the forest area. There we go. So there's different options in the duplicate tool for random offset, so they can be randomized or they can be gridded with perfect spacing. In this case, you could bring in a 3D model and then load in that 3D model as a DAE file, for example, and then fill in an area. So that's how some of these tools get used. The other optional tools, you could do a shadow query. So you could analyze a rooftop with different density and how, let's say, placing a building would affect the solar potential of that area. And these are all also exportable layers that have their attributes built in. Oh, that's the 3D model, sorry. There's the shadow query. There we go. So you can see the analysis for the date, the start time, the end time, the average shadow calculation. The other options in some of the tools, we have a buffer tool. So over here, you could simulate the location of trees. This is just a shapefile with points in it. See, it's just a tree sample.shape, and it's just a point file. But what we could do is treat those points as 3D models. And that 3D model could be different types of 3D model based on the attribution for type. So there's type 1, type 2, and then you could say, okay, type 1 is this type of tree, type 2 is that type of tree. And you could also determine their size, their scale based on attribution. You can have an attribution for size or rotation or canopy size. So it's really enabling GIS data to be visualized inside a 3D environment. So you can see we have different trees here with different heights, and we also have different types of trees. So this is tree type 1, and then it's going to load in tree type 2. So if you have, let's say, power line analysis and you want to do a buffer for that, this is the result of the buffer query. And the buffer query can then determine based on a given radius, you see if something is within a radius of that spot. So the ones that are marked red are have an object appear within that radius. The ones that are not don't have any obstruction. So that's part of the analytics that are available. And then the last thing that I'll review is, just a second, let me turn off this one. There we go. Is the photo inspector. So you could then visualize the images that were used to create the 3D model. Okay. Here we go. Make the icon a little smaller. And you could click on them in order to view the original image. Or you could click on the model. Let's say if I want to inspect this area or this window, I could set the filter by direction to only 90 degrees. 360 is if you click, let's say, on the rooftop, it brings in everything from a 360-degree radius. 90 degrees is for facades, so there's no point of viewing the image from this angle. You're only really needed from this angle. And then if I click on photos in point and click on this window, it loads a list of all of the available images that view this window. Here it is. And I can toggle between them, see which one gives me the perspective, the best perspective that I'm looking for. And here's a good example. I mean, looking at the mesh, yeah, the window looks okay. There is some, difficulty in correlating all these thin features, but looking at this lets you know that there is a shield around it, a net, not really a net, sort of a mesh, a metal mesh, rails that guard it. It could also be useful for, let's say, reading clear things that may get interpolated in the mesh, like license plates. If I click on this, I might be able to get a clearer picture of what's the best view. That one's a little far. Let me sort by distance. There we go. So gives you a clear view of the objects that you're looking at. Let's say over here, even though they get actually correlated very well in the 3D mesh, but if you do want the raw uninterpolated image, this can give you a very good option for viewing that. Okay, so I think that's more or less it. There are a whole lot of other things we could get into. There's a particle engine, so you can, create a fountain if you wanted to. You could simulate fire, smoke. There's a whole lot of different options for bringing in moving objects, aerial objects, building 3D shapes. And full compatibility also to bring in other 3D meshes from other software, or convert out the 3D meshes into other software, as well as modify them. So let's say if you have an area over here that you want to place and the mesh is getting in the way, you can just modify the mesh layer, mark the area that you want to flatten. There we go. And then flatten the mesh. And then you can place something else on top. So just the tip of the iceberg for all of the tools that are available. And I think that covers most of it.